All right. So I guess in the previous lecture, what we studied was something about particular differential equation. So again, not going into much of technical terms. So what we studied in general is how do I figure out the probability that I will go from some state I to some state j in the time period t plus h. And whenever I'm saying h, it is a very, very small interval of time. And in limit, we want that h to go to 0 always. And just give me a minute, guys. Yeah. So what we did was we figured out. So for us, it's always easier to figure out what's going to happen in a very short span of interval, right? Because we know there's not much that can happen. We can at max have one transition or no transition at all. So you either stay in the same state or you can only move in one different state. You cannot have more than two, at least in theory and at least in limits. And to hop onto two different states within that time interval h has a very, very negligible chance of happening. So it's really not, it doesn't make much of a difference, I would say, and when we take, at least when we take the limits. Okay, so we kind of came to a conclusion that the transition rate, so remember whenever I'm writing PIJT, I mean probability of transitioning from state I to state J in the time period T. So this T here represents the duration of the span that I have for going from state I to state J. And when I take a differentiation, it kind of means that this is the transition rate in theory. And we came to a conclusion that this differentiation is just equivalent to the probability that you go from some state I, which is provided to you in the question, and a hypothetical state that you assume k in time t, and then you multiply this with the transition rate that when you are at state k, you hop on to the state j in a very, very short span of time interval. And again, due to the Chapman-Kolmogorov equation, you know that this k exists, one for sure, and two, that this k can be anything. So you have to sum it up across for all the possible state space values that you can ever have for this k guy here. So I guess that was it. And then we also saw an example of our HSD, simple HSD model, where we couldn't really figure out the actual answers by solving this. But again, had we known these numbers, we could actually go on to solve this as well. But what we looked at was a very simple example where we didn't have three states, but only two states. So the number of equations that we had to solve were a bit less, and this calculation was a bit less tedious, I would say. Okay, so remember when I said to you guys that the method that we studied in the previous lecture is called Kolmogorov's forward differential equation. So there exists another method which is called Kolmogorov's backward differential equation. So again, remember, sometimes it's just easier to use one of these methods, but again, these two methods, however different they might be, they will always arrive at the same conclusion for the answer to the probabilities that we care about. So what's the difference between being forward and looking at backwards differential equation? So when I say that I'm moving from state I to an intermediate state k here in a span of time h, in a span of time t, what I'm doing is I'm going from I to k first. So I'm going from I to k in time period t, and then I transition from k to j. So I jump here from k to j in a very short interval h after I have come to a state k. So now what I'm going to do is, in the another scenario, what we will try to look at is the another case that's possible. So let us say Again, I have a same situation where I have to go from some state I to some state j, and what was the time here? I guess it was 0, and we looked at something in between, and we had t plus h here at the end, right? So here the difference will lie in what we consider first. So here what we are going to say is that when I'm going from I to j, I first hop on to some state k in a span of interval h. So because I'm starting from 0, this time is just h. So remember, this is the time duration and this is the exact time that I am reaching this state in. So there's a jump from I to k. And then I transition in the time interval small t from k state to j state. So that 0 to h and then h to t plus h. So if you do this kind of a calculation, you are kind of looking at Kolmogorov's backward differential equation. So this is just Kolmogorov's backward differential equation, I would say. So again, I don't think I'm going to go through the derivation once again. But if you guys remember, the whole concept of substituting in this Pij's h and everything will remain the same. But it's only the case that now this h term will come first and then you will have this t term. So let's say if we want to figure out the same probability, Pij t plus h, let's see what happens. So what I want to do is figure out the chance that I'll go from I to j in the time interval t plus h. So again, what I'm writing here within the brackets is t plus h, which is the whole time period that I have covered. So it does not matter if I start at 0 or if I start at, let's say, sometime s. If at the end I am at s plus t plus h, I have covered this much of time from where I started off. So I guess that is because we are looking at time homogeneous case. So the time that we start at does not matter anymore. Only the duration matters. Okay, so this will be what? Can someone try to come up with a similar summation that we came up with for the forward one, for this backward case? Can you guys try? Anyone?
So ma'am, summation over k, pik for the time interval h multiplied by pkj for the time interval t.
Exactly right. It isn't really much difficult. So what you have to do is you just have to multiply the probabilities that you go from I to k in time interval h, and then you go from k to j in time interval t. So I guess that's pretty much straightforward. And if you do substitute in the PIKH formula from the previous one, and if you take the limits and basically do some substitution and blah, 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 which I'm not going to do again, you can look at that derivation in the book if you want, or you can try it out by yourself as well, if you just want to do it for the thrill of it, I would say. Okay, so here the conclusion will be something similar. So again, you expect D of Pij to be here upon T of T. And what you will have here is summation K over all the state spaces that it can take. And then remember this PIKH, you will have certain terms like H times mu IK for this guy. And then when you divide it by H and you take limit H going to 0, the OH term will cancel out. And what you'll be left with is just mu IK. So this is the transition rate, the jump rate that you care about when you move from state I to state K in time period H. That is why you have mu IK here. And for PKJT, that will just be as it is. So you will just have PKJT here. And this will be your equation for the Kolmogorov's backward differential equation. but again in terms of metrics, I guess. So if I were to look at the same thing in terms of metrics, what I will have is d by dt p of t. So this represents the whole transition matrix here. And remember, when we are taking its differentiation, we are kind of looking at the transition rates. But again, this transition rate is not actually what you get. This is a multiple of the p of t here. So this is how you would write this in terms of matrices, or in just terms of the matrix P here. Any doubts in this? Okay, so maybe what we can do is we can go back here and we can try to figure out Kolmogorov's backward differential equation for the very model that we had a look at. So let us say I do the same thing again. So let me just switch colors. Okay, so now what I want to look at is d by dt PHHT. Okay, so how would this span out in case of backward differential? So remember, if I may just, so I guess what will help always is to draw this timeline. So again, you see you have a small time t. So let's say start from here, you have t plus h here, and you know you want to h here, and you're going from healthy to healthy state again. So what are the possible states that you can have in between here at time h? So again, what you would do is just sum for k taking value h as t. So again, these are the total values that it can take, but we know for sure, right, that if in time interval h you go from h to dead, then there's no way possible that you will move back to healthy by the time t plus h. So we know for sure that this d is not going to matter, but again, we'll just see what happens here. So what we had was mu mu h k, right? So you go from h to some state k here, and then you multiply this with the probability that you go from k to the state healthy again in time interval t. Does this make sense to you guys? Maybe I should draw something here. Does this make sense? So again, if you were just to expand it by this similar, just something similar to that, what you will get here is mu of, so now first we're going to try h as our k. So mu of h times probability that you go from h to h t. So this is something where you are staying in the healthy state throughout. You never transition to sick, you never transition to dead. So you started off at 0 time in h. By the time h, you are in capital H, healthy state, and by the time t plus h, you are still in healthy state. So this is something that you have. And so this is actually something known as occupancy probability, and that we will see again in detail in just in short time. So next up, we'll consider HS. So you have mu of HS, P of KS, and T, plus mu of HD, P of KD. Okay, no, it's not gonna be KD. It should be DH and in some time T. Okay, so now we aren't given these T's, but well, we do know about this transition rates, right? So can someone tell me what was the value of mu HH?
minus of mu plus sigma.
Right? It was minus of mu plus sigma. Absolutely. So if you have a look at, it's just, minus times the
second term, it should be, k should not be there. Right?
Oh yeah, K shouldn't be there. Oh wow, that's completely wrong. It should be, instead of K, I'm gonna write S, and instead of H, it's going to be H, because H to H, H to H, H to H, and DD, SS, HH. Yeah, I guess. Thank you very much, Mashita. Great observation. So what you will have here is PHHT, right? Okay, so now I want mu H plus S. What is that? Let me go back. Yeah, mu HS is just sigma, right? So what we have here is, instead of mu HS is going to be sigma, and again we do not know this probability. Okay. Now what do you think? What is mu HD? Anyone? What is the value of mu HD?
And it's mu, but P of HD in time t will be 0, so the whole term will be 0, right?
Exactly right. So this is going to be mu, but even though we aren't given the probability this, we do know for sure that to go from that to healthy state is just not possible, right? So this is just going to be equal to 0 by intuition. So then the rest of it, this will be your answer to the backward differential equation of this particular. So again, when I'm seeing backward differential equation, this down here and this, everything will be one differential equation. So you have derivative of PHH in terms of PHHT. But again, you can see here again, we have this PSHT. So you'll have to kind of figure out the value for this guy, a differential equation for this guy, and then let's say if you encounter something else, then you'll have to figure that out and then solve them simultaneously. So I'm not going to do that here, at least for this example, but I guess you guys should definitely try this by your own to write out the backward differential equation for PSHT. And I guess that is going to be something similar. But so, okay, so now if you have a look at this guy and that guy here, do you see some similarities? So again, remember we still have PHHT right here, and we have minus of mu plus sigma PHHT, which is same. But here we have sigma PSHT, and here we have rho HST. So despite these differences, the answer that you will get at the end, once you solve these simultaneously, will be the same. So the probabilities will coincide. And I guess that is the very beauty that this concept is based on. So this is forward differential equation. All right. Any doubts in the way we were solving for this backward differential equation?
No, ma'am.
Oh, I see Swapnil. Hi, Swapnil. How are you doing?
Yeah, hello, ma'am. Yeah, fine.
You're fine, I guess. I'm so glad to have you in the class.
Thank you, ma'am.
All right. So I guess now let us try to do this. And so, okay, now that we have already seen how do we derive our forward differential equations and backward differential equation for the healthy, sick, and dead model, we will go back to the thing that we started our chapter with, which is the Poisson process. So now we will try to derive these equations, again, forward as well as backward equations for the Poisson process. So again, remember, I think what I can maybe just do is draw the state spaces and remind you guys of the transition rate that we try to use. So again, it will kind of go on forever. And here, the probability that you will encounter one arrival is lambda. Okay, sorry, the rate at which you encounter arrivals is lambda, right? So this is the transition rate here. So we know for sure that if I'm looking at the mu ij, which is the rate at which a transition from state I to state j within a very, very short interval of time can only take 3 values. So again, it depends on where I land. So let us say if I'm starting at I, and this is the same as the state space j, which is where I find myself at the end of the time interval. So what rate should I be writing here? Anyone? Well, maybe to figure that out, we can also try to use metrics and plot and basically write the numbers that we will have for the generator matrix for the rates of transition. So we know for sure that the diagonal elements represent the transition from the state to itself. And one step after the diagonal, because in Posner you can only move one step ahead, you know that it's going to be lambda every single time, right? So let's say if this is the diagonal, then each and every probability beside the diagonal is for sure going to be lambda, right? And again, rest of these are just going to be 0. So again, not precisely 0 because you do have some negligible chance, but in limits we know it's just 0. So what do you guys think should be here in the diagonal terms? That is when your I is equal to G.
Negative lambda.
Negative lambda, right? So because as we know and as we have already proved that the rows of generator matrix should add up to 0. So here you have lambda and everywhere else you have 0. So here you will have minus lambda and so on and so forth. So whenever you start off in some state and you end up in the same state itself, the transition rate is going to be minus lambda. I hope that's clear to everyone. And now if my I is equal to j minus 1, or maybe I think it's better to write it in the, I think it's better to just write it in terms of j. If my j is I plus 1, that is if I move one state forward, one step forward, what do I get here? The rate of that happening is just going to be lambda, right? And then for any other case, I assume that this is going to be 0. And this assumption is the very nature of Poisson process. Any doubts so far? Okay, so again, whenever okay, so now I guess we have enough information to figure out the equations, Kolmogorov equations, be it backward or forward. So which equation do you guys think you want to start off with? Are you guys more comfortable with forward or are you guys more comfortable with backward equations? I guess maybe let's just start with forward equation. So what do we have here? If I'm looking at forward differential equation, and let us say I want to figure out. So instead of writing BPIGT, I can also just put a little comma up there and it will denote the differentiation. So I guess we have this. And again, maybe what we can just do is create this sort of a timeline that we used to do. So maybe I can create a timeline here. And now we know that we are looking for something to happen in time span of t. So what you will have here is 0. And here you can have t plus h. So again, remember, I'm looking at forward differential equation. So the jump happens at the last. So this is where the jump will happen. And this is where your t will sort of end. So, okay, what do you guys think I should write here? How do you guys think this will expand? I guess maybe the very first thing to do is write this as summation. Yeah. So the very first thing that we are gonna do is gate band kar dena. So the very first thing that we will do here is what? Do you guys remember? Hello. Can you guys guess what should I be writing after this summation here? And let us see, I write K here. What should I write after this?
And we'll take two probabilities, like from state I to K and then from K to J.
Right. So here I have I and I have J here. And let us say this is my K guy here. So I go from state I to K in time interval T. And then I go from state K to state J in time interval H. Right. Okay. And what all possibilities do you have here? So again, what I want to do is not only have a look at this. Okay, so wait, I guess this is not quite correct, right? Because what you said is Pijt plus H, and what we want is differentiation of this guy, right? So it will have one term where you observe a jump in terms of mu, and the other term which will be in terms of probability. So in this case, we know that jump is being observed at the end. So what you will have here is mu k j, and again I think it's fine even if you don't write h there, because you know that the time interval is just h. Does this make sense? So remember, I'm not writing Pigt plus h, I'm writing the differentiation of Pigt. Okay, so now that we have this, we want to figure out what all states are possible when I move from I. So let's say if I'm moving from I to K in some time period T, what all states are possible? So again, I guess the very first thing that might come to your mind is these possible states, right? So again, why do I think that these are the possible states that will come to mind? Because if let's say your K, okay, maybe let me just take another example. So you know for sure, right, that in some small time interval, you can only go from 0 to 1. You cannot go from 0 to 2 in the time interval h. And at max, you can stay at 0. So these are the only two possibilities. You stay at 0 or you go to 1 in a very, very short time interval h. So here what we want to do at the end is move from state k to some other state j in that very short span of time interval. So we know for sure that either this thing, so this thing should either be j or this thing should be j minus 1. Do you guys agree with what I have just written here? So because I want to hop on to j at the end, I know that I can either be at j or j minus 1 in the previous state, so that I can literally hop on just to where I was, or maybe one step further, which will be j minus 1 plus 1. And that will give you the j that you have here at the end. So here, if I may just write this thing again, I know what I can rewrite this thing as. So again, I know that these are the two plausible considerations for my state k here. So what I will just do is p of I to j. Let us say for now I just write it as j, and this happens in time interval t. And here I will have mu j plus p I j minus 1 in time interval t and mu j minus 1 to j. Okay, and now we know for sure, right? J to j, even though we do not know what state we are at, we know that we stay in the same state. And the probability of that happening is minus lambda. So you can easily substitute that in here and you will get minus lambda times Pijt plus lambda times Pij minus 1. Does this make sense? Okay, I forgot to write the t here. Does this make sense to you guys?
Can you repeat the last situation?
Can I repeat the last sentence? Okay, so what I said was, I have just substituted in the values. So the value of mu jj is just minus lambda, and the value of mu j minus 1j is just lambda, right? And this you get because you're hopping one step forward. So your I is j minus 1 and your j is j. So this is where it comes from. And this is where the other thing, where you stay in the same state that you started off with, comes from. Did you ask this, Vanshika, or were you asking something else?
No, same thing. I got
Okay, you got it? Okay, any other doubts? Savri? Swapnil?
No, ma'am, it's clear.
It's clear. Okay, but now what we know is, let me have a look at all the possible states that my Poisson process can have. So if I were to list out my sample space, I can literally start from 0, 1, 2, and so on, right? There's no end. But I know that if I'm looking at P00 T, what is the chance that I start at 0 and that I find myself back at 0 after some time interval t? So first of all, you might think this is impossible, but again, we know for sure that if I stay only at 0, let's say after every single time I'm only staying at 0, no one enters in my cafe, let's say today. So there will be 0 customers by the end of the day, right? So you know that there is still a possibility that that can happen. And if you try to use this formula, what you will get here is 0 minus 1, which does not make sense, right? Because minus 1, we don't have that in our sample state space. So what you can actually do is, for the sake of completeness, you can say that this is true for every time you're looking at j greater than 0. And also for the times when you have your j as 0, so let me just maybe use another color. And what I'm going to write here is pi0. So that means I want to end up in state 0. And I'm looking at the time interval t here. So again, I think we know intuitively that the only possible way I can find myself at 0 at the end of some time is if I never leave the state 0 itself. So, but again, if we try to use this formula, what you will get here is summation k belongs to S, P I k t, and mu k 0. And you know that the only possible value of this k is 0. So because mu 0 is going to be something other than 0. All the other values of k will render you a transition rate to 0 from that particular state as 0. So what you will have here at the end is simply pi. So instead of k, I'm going to write a 0 here, because we have come to a conclusion that 0 is the only possible k that we can ever have in this situation, which does not have a probability of 0. So here I'm going to have mu of 0, 0. And I know that my mu 0, is just minus lambda. So this is going to be pi 0 t. Does this make sense? So maybe I can just write here that right? Because there's no other possible way you can actually move and come back to 0. So remember, why was that the case? Only because we're looking at the Poisson process, and we can only add 1. You can never subtract 1. I mean, you can never make a customer who has already entered your cafe as someone who has not ever entered. So I guess that should be clear. But again, now this was about forward differential equation. I want you guys to try by yourself and try to come up with the backward differential equation for the very same case. So I want you guys to first create a timeline, which is, I guess, very helpful, and then see that, so remember, in forward differential equation, we're looking at what? We look at the last jump. The jump is at the last, right? So you jump at the very last of the stage. That is why you want this K to be something where you can hop on to the state where you want to reach at. But again, if you are looking at the backward differential equation, what you will look at is the very first jump. So you want your K to be something where you can land up from this I. So now let us try to derive the backward differential equation for the Poisson process. So I'm again going to look for P-I-J-T prime. So what do you guys think I should write here? First of all, I think I should make a timeline, right? Because that makes everything easier for me. So 0, I know this should be my h, and here I am at I, and this is, let's say, my t plus h. Here I am at j, and this is my t time, and this is my h. All right, so let us denote this h by k state. So what do you guys think I should write here? We'll go step by step. So first of all, I guess we should resort to writing this for our backward case. So who will help me out here? Come on, I guess the first step should be easy, right? You don't really have to do anything. This is the common state in every process that you look at. So who would like to dictate this step?
Summation K belongs to S.
Same with just H instead of T.
Yeah, and what should I write next?
Mu I K, and then probability
Yes.
of J from K in time H or T time T.
So from
K
T to
time
J in time T, right? Okay. So now what we want to figure out is, what if I'm starting at I, what are the possible values of K that I can have? So I guess I shouldn't write. If I start at I, the possible values of K are I itself and I plus 1, right? You can either stay at the same state or you can move one step forward. Therefore, you can rewrite this thing. I'm just going to write this again. So again, first you wanna just write it as I, and here you will have Pij T, and for the next step you will have mu of I to I plus 1, and Pi plus 1 comma J T, right? And what do we know now? We know this mu I and mu I plus 1. This is just minus lambda Pij T, and this is just lambda Pi plus 1. So this is I plus 1 comma J in time T. So now if you have a look, you do not have any limitations here, right? Because even if your J is 0, or let's say even if your I is 0, you have valid probabilities everywhere. So this is the only backward differential equation that will suit the solving of this probability. Any doubts in this? So I guess now you do not even have to remember the formula that we had a look at. What you just have to do is figure out this timeline. If you have forward, you look at the last jump. You look at jump at the very end. And if you're looking at the backward differential equation, you jump first. So that is the only difference. And again, these equations might look very different, but they'll give you the same answer. So I guess that is how you write and derive basically this differential equations for the case of Poisson process. And if you look at the past papers, I would say nowadays, given that you guys have multiple choice questions, they do not specifically ask you to solve these. So again, this is only one way of figuring out the probabilities. There is another method. So in this method, we used differentiation, right? We are looking at Pij prime t. And there is another method wherein you can have a look at the integration and you will essentially get the same answer. But to solve that integration manually is a bit not quite possible. So that is why if you are asked about differential equations, then you might have to solve it, because solving this is possible, at least with the two methods that we have discussed earlier. So let us try to move. Okay, first of all, any doubts so far? Till I move on to the next topic. Okay, so I'm taking that as a no. And I guess even before we discuss the next topic, let me just ask you a very basic question. Let us say we have our very own cafe, and to make this assumption plausible, let us just say that, there is only one seat available in the cafe. So at one point in time, you can only serve one customer. You cannot serve more than one customer, and you cannot even start preparing for the other customer until the current customer leaves the cafe. So this kind of summarizes the assumption that at one point in time, you can only stay in one state. So here, the number of customers that you can have in your cafe can only be one at one point in time. And if you accumulate it over a day, I think it can be many. So let me just ask you guys, let us say if in 1 hour, so in 1 hour, 10 customers arrive at the cafe. So now I've said that in 1 hour span of time, you have had 10 customers arriving at the cafe. And if let's just say that this is valid every time else as well, and that the customers are uniformly distributed. So when I say that the customers are uniformly distributed, what I'm trying to say here is that there is no dependency between the customers arriving, and that these are independent, and that these span over the equal interval of time that these all might spend in the cafe. Okay, so now if I ask you guys a question, what is the average time you expect a customer to spend or stay at the cafe? So again, this is a very general logical question, right? There is nothing that we have studied of any sort that you would want to know to answer this question. What do you guys think? Okay, so let me maybe just put another assumption that the cafe is never empty. So there's always one customer or the other in the cafe. It's never empty.
minutes.
I couldn't hear you well.
I said 6 minutes.
Okay, so I heard someone said 6
Are you saying
minutes.
that a customer will spend in a cafe? It's 6 minutes.
Yeah, is that, and who was that? Savi? Was that you?
Yes, ma'am.
Okay, yeah, that is indeed correct, right? So do other people agree with Savi?
Yes, ma'am.
Okay, so now okay, so Savri, I want to know what did you do to arrive at the answer 6 here in this case?
Ma'am, I just used exponential distribution.
You used exponential distribution, and how did you use exponential distribution here?
Ma'am, we have been given like 10 customers, so that the expected value of X is like it is a waiting time period, right? So we can consider exponential. So the mean will be 1 by lambda, which is 0.1, and then into 60, so 6, like for.
Okay, okay, that is one method. Yes. Is there any other method that you can use? So forget about the fact that we have proven that the waiting time follows exponential distribution. I never really said that, these, okay, but yeah, it kind of satisfies the assumptions of Poisson process. So this is indeed a correct method, but this is a very sophisticated method. I want you guys to think of it in even simpler terms.
And very basic, we can answer like there are 60 minutes and 10 customers are arriving. So like directly going, we get 6.
Right? So 60 minutes, 10 customers. So how much time? One for one customer, right? And what you will do is just cross multiplication. So to figure out this question mark, you will just have 10 upon 60, which is what? 1 upon 6. So you expect one customer to take up 1/6 of the time. Is this what you mean? Can you guys see the flaw in what I've done here? Yes, Vanshita?
Would be 60 upon 10.
Vanshita, I cannot hear you well.
It would be 60 upon 10, no?
Why do you think it will be 60 upon 10? I wanted to figure out this question mark here, right? Oh, yeah. Oh, okay. Sorry. Wow. Yeah. Thank you very much. Wow, I'm surprised at myself. So we have to figure out this question mark, and what this will be, just 60 upon 10, and you get the answer as 6 here. So if you assume that 10 customers take 60 minutes, you can kind of come to a very basic conclusion using this, that one customer will just stay in the cafe for 6 minutes. So this is something that we will try to derive now using the sophisticated method. I mean, we are not going to derive it specifically, but we'll have a look at this thing again in terms of the Markov models that we just looked at. So we'll try to figure out the time spent by these lives in, let's say, healthy state, in sick state, I mean, in death states. If they go there once, they're going to stay there forever. So I guess that's fine. So let us move to the next topic, which is very, very interesting, I would say. And that is called holding time, waiting time, or the occupant probabilities. So I've spoken about the occupant probability already, but let me just mention briefly some results here. So let's say if I want to figure out.
Ma'am, just a question.
Yes, Vanshita.
For the previous, can you just, yeah, so here we just have one assumption that cafe is never empty, right?
Yeah.
So we have not assumed that there's only one customer in the cafe, right? So practically this, isn't it a bit weird?
Okay, so I don't know if you had some issue or maybe if there was some issue on my end, but even before starting this, I did assume that there is only one seat in the cafe. You cannot stand or cater to more than one customer in the
Okay,
cafe.
I didn't hear that actually.
Yeah, so I guess it's
Was
fine, but yeah,
asking.
that at least got you thinking. I'm happy. I'm glad that you asked. So I guess now that's clear. So now what we are trying to look at is the distribution, not change of color I had. So what I want to care about is the distribution of this holding time so that I do not have to do the complicated stuff again and again, and I can have a generalized result and I can just put in the value. So let's say if I have a question, what is the chance that this life will be in healthy state for another 20 years? So what I will have to probably do is probability that this life will stay in healthy for, let's say if I'm starting at healthy at time 0 and this will just be 20, right? So you might want to just figure this thing out, and sometimes you can also use different random variable notations to denote the time that you spent in a particular state. So we'll see how do we denote that, but let me just start off by saying, okay, let me just say that, let us say that okay, so first some notation. What we are going to look at is the distribution of holding time, but let us have a look at the distribution of first holding time. So x0 denotes the state that you were in at time 0. So here x0 denotes the state at time 0. So whenever you leave this particular state, so let's say x0's value is I for now, you know that for the very first time when the value of this x0 will not be I is when you will have left that state, right? So let us say you start off in the healthy state. In the next time period, you are in healthy. The third time period, you are still in healthy. The next time period, you are still in healthy. But then the very next time period, you get sick. So you move from healthy to sick. And that time period is what I want to call as T0. So when I'm saying T0, this is, so I'm going to write INF here, which is a very technical term. But for now, you can also say that this is the minimum. So the minimum time T when the state at which you are in XT is not equal to X0. So if this happens in the very first step, let us say if your X0 is healthy and if your X1 is not healthy, then this T is going to be 1. And this, what is T0? T0 is again going to just be 1. So this T0 is the value of this small t here, which comes from this small t here. So this is just one thing that I have now defined, and that is T0. So my T0 is the first holding time. So I know that at T0, I go from healthy to sick. So from 0 to T0, I was in the healthy state. So this is your first holding time. Any doubts in this? So again, I mean, just to kind of give you guys an example of what's the difference between minimum and infimum. So sometimes minimum may not always exist. Let us say if I give you guys this state, let us say my A is 1 to 8. What do you guys think the minimum value of this set is? Anyone? So let me just maybe change the question. If I write something like this, what do you guys think is the minimum value that A can take? In both cases. Anyone? So what is the minimum value that A can take in this case, where A takes any values from 1 to 8, inclusive of 1 and 8? Hello? Am I audible? Can you guys hear me? Vanshita, did you try to say something? Because I couldn't hear you.
You said yes, we can hear you.
Oh, okay. So the minimum in this A will be 1, right? Because this A can take values starting from 1 till 8. But here I know that 1 is not in A. 1 here does not belong to A. And the minimum value that this can take can be anything. I mean, I don't know. If I say that the minimum value is, let's say, 1.11, I could still write something as 1.01, which is less than this and still fits in A. And if I say that this is my minimum value, I can still add another 0 here and say that, okay, now this is less than this, so this should be the minimum of this set. And you can do this and you can basically play this game forever, right? So in such cases, you use infimum. And infimum here in this particular case will be 1. So whenever I'm talking about infimum of A, my infimum did not belong to A always. And it's just the greatest lower bound that you can have. So there will be no value less than 1 that you will ever observe for this A guy here. So this is just a bit of a technical introduction to the infimum. And there's a complementary concept to this known as supremum, which will be for this 8 guy here. So here maximum will be 8, but here the maximum will be, you can't possibly say, right? Because if I write 8.99, you can say it is 8.999. Which is greater than this and still lies in A. And if I say this, then you can again say this is 8.9999. So again, what helps is to just define one supremum and you can write it as SCP sup. So sup of A in this case will be 8. And again, that 8 does not necessarily shouldn't necessarily belong to the A set over there. Okay, so now that we have defined the distribution of our first holding time, now that we have defined our first holding time as T0, it's time we look at the distribution that it might follow. So to have a look at the distribution, the very probability that we care about is the probability that this T0 is greater than some placeholder T here, given that you have started in some state I here. So you're kind of seeing in this probability that at time 0, you are starting off in some state I, and that you stay in the very same state for at least T period of time. So your T0, which is the very first time you leave this state I, should be greater than T. So you know for sure that T is the minimum time that you spend in the state I. So this is again exponentially distributed. So I know that the PDF of exponential is something 1 minus e raised to minus lambda x, but here I'm looking at T0 being greater than T. So it's going to be 1 minus this thing. So this becomes plus and so on. So what you get here is e raised to minus lambda T. But again, here it's not just any lambda. You will have lambda I. So what does this lambda I represent here? This is the total force of transition out of state I. So let me define lambda I here. So this lambda I, which is the parameter for the exponential distribution, is equal to minus mu I, or else it could also be equal to summation of mu ij, where j is not equal to I. And again, this holds because of the fact that mu I plus this summation mu ij, where I is not equal to j, is equal to 0. So this lambda I guy here represents the total force of transition out of state I, which is quite evident with this, right? So you're moving from I to j for all the times where j is not equal to I. So this is taking into consideration all the force of transition that you have from state I, but not to the state I itself. So let me just write here that this lambda I represents the total force of transition from state I. Any doubts so far? So again, the proof of this you don't have, but I guess what might help you to visualize this is the comparison that you can draw in between POSMA process and these processes, with the only difference being that in POSMA process, you can only go one step forward, right? You can only go from 0 to 1. You can never come back from 1 to 0. But in the general scenarios and in the general situation, you can come back. If you, let's say, go from healthy to sick, you can again go back to the healthy state once you recover. And let's say if you go to dead, you can never go back. But there is still a possibility that you might move back. So that's the only difference. And that doesn't make much of a difference because of the Markov assumption that we make. So what has happened in the past does not matter. It does not matter if you are in the healthy state, if you were in the healthy state in the previous state as well, or if you have come from the sick into the healthy state today. I mean, ideally it should matter, but if you're looking at the time homogeneous case, and if we want this to follow Markov property, this shouldn't be the case. So now that we already have defined our first holding time and the distribution, if I asked you guys a very simple question, that what will be the expected value of the first holding time in state I, what would your answer be? So I guess what I'm trying to ask is the expectation of T0 here, right? Because that is the first holding time. So expectation of T0 is what? So here we have already defined that T0 follows exponential distributions with the parameter lambda I if we are starting at state I. So here, if you're looking at the expectation of T0, what will it be? Anyone?
1 by lambda I.
1 by lambda I, right? So that isn't it correct? And this is just 1 upon lambda I. So if you kind of move back and see the connection between the example that we discussed here and what I have derived here. So the expectation of T0 is 1 upon lambda I. So here, what is my lambda I? So Savri, I guess it was you who used exponential, right? To figure out the answer to this over 6 minutes. So it was 1 upon 10 upon 60, right? So 10 customers in 1 hour. So 10 upon 60, that would be your rate of customers arriving in a very short span of time. And if you do 1 upon that, you get 6 here. So you get 6 minutes as your answer. So I guess, I mean, the very thing that we have derived here formally, we already knew that from this example. I guess this is just to show you guys because we aren't going to prove that this T0 indeed follows exponential with lambda I here. So now that this is clear, this was all about the first holding time. But again, now that is not all we will be concerned with always. So again, this does not matter. So what we said here was that this x0 is I, and this t0 is the time, this is the time, this is the minimum time that you spend in the state to which you started off at time 0. So now what I'm instead going to do is a bit of a derivation to check how can we come up with the probabilities if we know the transition rates and the waiting time. So let us say if we know that 6 minutes is the waiting time for each customer and the rate of arrival for each customer, then you can figure out how many customers you will have by some time that you specify. So I guess maybe even without going through the formal proof, let's just discuss the result first and then we can go through the proof, I guess. So let me just say that the probability that you are at state I in time 0 and in time t0, which is when you make your first transition out of state I, you go into state J. So this is going to be equal to mu ij upon lambda I. So to figure the probability that you will move to state J from state I in some time t0 is just equal to the fraction of the transition rate from I to J upon the waiting time that you expect the process to be in a particular state I. So again, if you go back to figure out what this lambda I is, it is the total force of transition from state I. So what is this? This just denotes how much of a rate you have to move from I to J if you can move from I to any other state J, right? So any doubt in this?
Ma'am, you're on mute.
Okay. Sorry about that. So what I was saying is if this is not that intuitive, maybe let's just try to derive it formally. So I have this number line where I am at state I in time 0 and in state J at time t plus h. So now the probability that I want to figure out is this. The probability that at t plus h, I find myself in state J. And this is given that I started off at state I. But again, there is something else. So one condition that I want to put on is that the holding time that I see for myself to be in state I is greater than t and less than or equal to t plus h. And again, the very fact that I'm saying that this holding time should be less than or equal to t plus h is because that is the time when I reach state J, right? So my t0, which is the holding time, it should be less than or equal to t plus h, always. So this is kind of intuitive and this is already implied. So I can ignore this condition and this probability due to the very fact that I am in state J at t plus h. I do not need to say that this holding time for my 0 should be less than or equal to t plus h because it's kind of implied. So this will just be equal to x t plus h being equal to j such that t is less than t0 given that you start off in state I. Okay, so this is what you have. But again, if you go back, this is the probability that we know. So what is this? This is that t0 is greater than t, given that x0 is equal to I. So what we'll do is, we'll try to recreate that scenario in this case here. So maybe what we can do is, I can write whatever I have in the numerator here as it is, xt plus h equal to j, given x0 equal to I. Okay, but what I also want is something like this. So probability, because this is what I know, right? Given that x0 is equal to I. So I will multiply and I will divide here with the same thing. So here now I can be consistent with this notation. It is just the same thing, not much different. Do you guys agree with what I've done here? Does this make sense? You can take some time. Any doubts so far? Okay, so what I can do is, instead of trying to solve this thing in this weird notations, what I can just do is define this as A, this as B, and this as C. So what I have here is probability of A, comma B, given C, upon the probability of B, given C. And now I want to see how I can simplify this expression right here. So maybe what I can do is, I can write this as A, comma B, comma C upon the probability of C. So this is just the numerator part. And this will get multiplied by the probability of B, comma C upon the probability of C. So this and this will just get cancelled out. And what you are left with is something like this. And this can also be written as the probability of A given B, comma C. So now you use this as your guide to figure out what you should write for this guy here. So what you will have is probability of A, which is xt plus h being equal to j, given t less than t0, comma x0 being equal to I, right? So this is what we have derived, and this will come as it is. So maybe what we can do is, we can just replace this thing as e raised to minus lambda I t. So I've just used what we derived earlier. And now, does anyone know how can I rewrite this probability? So maybe what I can, so what I'm seeing here is that at x0, I start off in some state I, and then I stay there for at least t time interval. And then I find myself at state j in h after t. So what I'm going to do here is do a bit of a change. So this stays as it is, but to the conditioning that I'm going to do, what I'm going to do is generalize this thing. So here we were looking at state 0, but now what I'm trying to say is something about the time when we are in the state I itself, forgetting that we are starting at 0. So I'm just writing that xs is I. So at any time s, I find myself in state I. But again, this s cannot exceed t plus h for sure. And if I were to say strictly, this s should be greater than equal to 0 for it to be a valid time. and it should be less than or equal to t, because t is the time that you spend in state I, and this is that represents it should also be less than or equal to t, which we have here, and this will come as it is. So e raised to minus lambda I t. And now that we have this in terms of s, t, and t plus h, we can kind of summarize this thing as just the probability. So again, you are in state I up until time t, and you only find yourself in state j at time t plus h. So what is this? This can be written as the Pij in time interval h multiplied by e raised to minus lambda I t. And now, just to make it a bit of intuitive, what you should rather do is just multiply and divide. Okay, maybe I should do that on the next page. So now what we're going to do is divide by h and take limits h going to 0. So what you will have here is, so PIH when h goes to 0, and if you take the limit, it just becomes mu ij, right? And that will be multiplied by what? It will be multiplied by e raised to minus lambda it, because there's no h term here. This will never get affected. And now this is the answer that you have. So what I can maybe do is just divide this thing by lambda I and multiply this thing by lambda I e raised to minus lambda it. So this is essentially the same thing, but now what I have here is the PDF of the exponential, right? And rather I should say the PDF of holding time, which is just exponential. So this represents the density, the value that it takes, and this is the probability that you move from state I to state J. So this is basically the probability that you jump out of state I into J, which is what we saw previously here. So this is a very important result, I would say. Yeah. So any doubts so far? I guess, see, you will never have to remember this derivation. The only thing that you have to remember is these probabilities. What is this probability? And again, this is very intuitive, right? And the only next thing that you might want to remember is that the distribution for waiting time for holding time is exponential. So maybe what I can do is we can summarize our results here. So results. So let us say I denote my waiting time as Wi. So if I'm denoting Wi as the waiting time or holding time or whatever you might want to call it, then my Wi follows exponential distribution with the parameter lambda I. So again, whenever I'm saying Wi, it means the time I expect on average to stay in the state I over a long period of time. And therefore, probability that you will stay in state I for a period higher than t is just going to be, okay. So again, remember when I'm talking about PWI being greater than t, what I am indeed talking about is something this. And let me try to just write it first and I'll explain you what is the importance of the bar that I have put in here. So the bar that I have put in here, so let us say if I were looking at the probability that I stay in the healthy state for time t at least. So that would mean that I cannot go from healthy to sick in between and then come back to healthy by the time t. What it means is that I stay in the healthy state forever throughout the whole span of the time interval that I am concerned about. So this is what you say is occupancy probability or occupant probability. So you can never leave state I. You never leave I. You always stay there throughout this time. Or else if I just say that, at time 0, I am in healthy and I want myself to be at time t again in healthy state. So that would still be PHHT, right? And what could happen is in between that, you can go from healthy to sick and then come back to healthy state. So that is not what we are counting here. We are talking about the waiting time. How much you have to wait in the healthy state before you move out to sick state. So that means that you stay in the healthy state forever. And I mean, forever by mean forever of the waiting time that you have. So that is why you have this bar over here, which just denotes the occupancy. So basically it just kind of denotes that you have occupied the healthy state for the waiting time period. Any doubts in this? So you might only want to remember the results that we have derived, and it's fine even if you do not bother with the derivation, but it's good if you find some intuition from the derivation. Elsewise, I guess what we should now do is try to solve one example. So remember in the previous lecture where we were trying to solve some sums from the end of the chapter of, I guess it was chapter 2, there was one sum which was a bit trickier. So this is what we should ideally study before we solve that sum using the other method that we didn't quite cover in the class really that well. So today we are going to study the expected time. Maybe I should just write it here. Why we used all of this piece? Okay. So what I care about is the expected time to reach some state K from state I. So this is what I want to know. How much time do I expect to move from a healthy state to sick state in the first place? So I guess what's going to happen now is, again, just a bit of notations, introducing some new notations. So let my MI denote the expected time it takes for the process to reach K when you start in the state I. So let's say if you start in I. So my MI denotes, so again, here it doesn't involve K anywhere. It just denotes the state where I'm starting from, because I know for sure that the only thing I care about is reaching into the state K. So this MI denotes the expected time it takes for you to reach K if you start in the state I. Then now if I were to figure out the formula for this MI, I know I do not know the actual value of MI as it is, but what I can maybe say is it will be the addition of certain terms. The very first thing when I'm saying, so let us say that my K is sick and currently I'm in the healthy state. So the time it will take for me to go from healthy state to the sick state is what I want to figure out. So what will this be? First of all, we will add the time that you expect to stay in the healthy state itself. Because for that time as well, you do not go into sick state. So you have to take that into consideration. And we have just derived that it is 1 upon lambda I. So this is the time you expect to hold yourself in the state I. So you hold yourself in the state I. And once you have added this, The next term that you will add, which let me just write first, is mu ij upon lambda j. This is lambda I times mg. And here your j should just not be equal to either I or k. Okay, so what I'm trying to say here is, so okay, first of all, this mj denotes what? This mj denotes from j to k, right? The expected time it takes you to reach state k once you are in state j. So what you're doing is, maybe not in the healthy, sick, dead model, but just for now consider that it is healthy, sick and corona model. So instead of dead, you have corona. So, and sick is not considered corona. I mean, that's just the assumption that I'm making. I'm the god of this sum here. So what I have defined is healthy, sick, corona. So you can go back from corona to sick, and basically you can move back from any other state. Okay, so now I want to figure out how much time do I expect myself to reach to the sick state if I'm starting at the healthy state today. And what this formula says is, so the very first term adds up the time that I spend in H itself. Then what I'm doing is I'm adding up the time when I go from H to any other state than S and H itself. So what I've done here is I've taken J not equal to I and K. So K is my sick, which is my end goal, right? And I is where I'm starting off from. So I'm taking all the other possible states where I can go from my I, and then the time it takes for me to reach to the sick state once I am in this particular state. So here what I've done is, you will have mu of hc upon lambda h, the whole probability that you will move to corona once you are healthy, and that you multiply with the time that you expect to take for you to reach to sick when you are in corona state. So this kind of summarizes the all of time that you will take to reach sick state from being healthy. Any doubt in this? Okay, so I think maybe what we can do is we can have a look at one example wherein we'll use this formula to derive these expected times. So let me just write here example. And what I'm defining is that this is my healthy state, this is my sick state, and this is my terminally ill state, where if, let's say, I am in this state anytime, I am bound to be dead. There's no way I can recover if I'm terminally ill. So this is 0.05, this is 1, remember these are rates, so yes, it can be 1. This is 0.02, this is 0.15, and okay, you can be dead. And this is 0.40. So this is the whole model that we have. And the very first thing that we are supposed to calculate is the expected holding time in state S. What do you guys think this should be? Anyone? What is the time I expect to spend in state sick if I am in that state once before I move out to any other state? Anyone? Are you guys there? Savri, Swapnil, Vanshita? Can you guys hear me?
Yes, ma'am.
Yes, ma'am.
Okay. So again, from what we have discussed today, do you guys want me to go back to the slides? Or are you guys trying to come up with the answer for this? So, okay, let me just do a bit of a recap. Yeah, so this is about the holding time, right? And what did I say? That my lambda I here represents the total force of transition from a particular state I. And the expected holding time is denoted by 1 upon lambda I. So this is the result that you will use to figure out the expected time you will spend in the state sick, and that will be 1 upon lambda S. And again, what is lambda S? Lambda S is the total force of transition out of state I, state S here. So what you have here is, so from S you can go to dead, which is 0.05. You can move back to H, which is 1, or you can become terminally ill, which is 0.15, right? So if you add all of this up, you get 1.2. And that is your answer. And I guess if you translate this, so again, these rates, so let us say in the question, I also mentioned that these rates are per year. So then you can say that 5 by 6 years. And this is how much time you expect to be put in state sick. Does this make sense to you guys? Any doubts before I move forward to another question? So I don't get a yes and I don't get a no as well. So I'm a bit confused whether you guys have understood or not.
Yeah, ma'am.
Okay, Savi says yes. What about the rest of you?
Yes, ma'am, got it.
Vanshita? Is this too much for you in a day? I guess maybe she's not here. Okay, so now the next question is the probability that you will move to dead when you leave sick state. So now going back to the formula that we will be using to figure this thing out is this, right? This will be the formula that you will have to use. Jumping out of state I into the state J. So the probability that you will jump out of state S into the state D. So now can you guys tell me what should I write here? So this is going to be mu of S to D upon total possibilities of moving out of S. So mu SD is what? Is this 0.05? So this is going to be 0.05 upon 1.2. Does this make sense to you guys? So that will be your answer to the part 2. Okay, so I guess now this part is very interesting. And this is where we'll be using the last formula that we studied, which was about the expected time that it takes for you to reach state K if you start from state I. So remember, I mean, you do not have to remember this formula. This is given in your table booklet. I think the only difference in your table booklet they have used is, I mean, they have sigma ij instead of mu ij. So, but I guess it just denotes the same thing, transition rate itself. Okay, so now my third question is, what is the expected future lifetime of a healthy life? So now I want to know from you guys, what do you understand by this question? Where all you can go, okay, so which all states you think you can go from healthy state to figure this thing out? Anyone?
Every state except dead.
Every state except dead. Okay, so let me ask you another question. If you go from healthy to sick, and then you go from sick to terminally ill, is there any chance that you will be healthy?
No, only sick.
No, right? Only sick, right? Okay, so I guess that is done. But again, what can also happen is, I mean, you could have possibly said this, that not always, if you are a terminally ill person, you will be dead. You can be terminally ill forever, right? You can ideally, in theory, be terminally ill forever as well. So there are these different possibilities that we might consider. But first, let us try to use the formula that we have to figure this thing out. And again, what we are trying to prove, what we want to calculate is the expected future lifetime of a healthy life. So for how many years do you expect this life to at least not be dead, right? Because that is all the times he or she is alive. So maybe what we can do is we can denote by MI the expected future lifetime of a life in the state I. So let us say if I should maybe just write it here. So I'm using MI to denote the expected future lifetime in a particular state I. So I haven't said that my MH, I mean, I haven't said anything about MH, MS, MT, but in general, I've said that I expect my MI, I'm denoting my MI as the expected future lifetime in state I. And now what I can do is, I can use these, I can create these equations multiple times. So I know if I have MI, I will get the equation of MI in terms of MJ, which is, let's say if this is H, then this will be S, T, or D. And then if you have a bunch of these equations, maybe we expect that we can solve them simultaneously and get somewhere and figure out MH at the end, which is our answer. So what we want to figure out is MH. What is the value of MH here? Okay, so let us try to first write the equation for MH. Again, it is 1 upon lambda H, right? So maybe we can try to figure out the lambda H first. What is my lambda H? It is the sum of all the transitions out of state. So I can maybe be sick or be dead, right? So my lambda H is 0.07. My lambda S, we have already figured out, is 1.2. My lambda T is what? You can only go to this. So I guess this is just going to be 0.4. And lambda T, I guess this is not gonna matter because it's just nothing. Okay, so now that we have this, we can easily try to write the equations. So if I want to write MH, it will be 1 upon 0.07 plus some things, right? So first of all, we have to figure out where all you can go from state H. You can go to state S, you can go to state D, right, from H. So what is the chance that you will move to state S? So it will be the transition mu HS upon lambda H, which is 0.07. And this will be what? 0.05 upon 0.07. But again, what does my MD represent here? My MD represents the expected future lifetime in state D, which is what? 0. So this does not matter, and this is the equation that you have. Okay, and again, now what you will do is you will rewrite the same equation for S guy here. So let us say if I write my MS, it will be 1 upon 1.2 plus, where all I can move from S. I can go to H and I can be that. So if I move to H, the chances is 1 upon 1.2, and here you will have 0.15 upon 1.2. But again, sorry, this is, again, we will not consider MD. What we will consider is MT. MD is again 0. So it should have been 0.05. But again, MD will just be 0. So I'm not going to write that again here. So this is the equation that you have for MS here. And again, what you can write is the equation for MT, which will be 1 upon 0.4. And again, the only thing you will have here is MD. And as we know, MD is 0. So I've ignored the MD terms here as well as here. So you have 3 variables, MH, MS, and MT. And you have 3 equations. So I guess you all can solve these equations together. So you know the value of MT, you can substitute in here. And then you will have 2 equations in MH and MS. And I believe you guys can solve these to get the value of MH. And I think that you guys can take as your homework. So what you will have to do is solve for MH. And the value of this thing should be 19.18. And that is the expected future lifetime of a healthy life. Any doubts with this question? Anyone? So what we did was, we tried to use everything that we just studied. We had this model. We were supposed to figure out how much time do you expect yourself to be put, how much time do you stay put in state sec? And that is just 1 upon lambda s, where lambda s is the total force of transition out of the state sec. So again, I guess this is a bit intuitive as well, right? So what is lambda s? Lambda s is the rate. It's a summation of all the rates where you go from state S6 to some other state. So if the rate of transition to some other state is very high, then you expect to stay in sick state for less time. And that is why you have 1 upon lambda S here, which does confirm that relationship once again for us. Then you were supposed to just figure out the probability that you go to state dead when you leave the state S. So what you did was you figured out what is the rate at which you leave from sick to the state dead. But then that is not all. You also have to figure out all the possibilities where you can go from state sick, which is counted by lambda S. So you have this as the probability that you go to D when you leave S. And then we figured out the expected future lifetime of a healthy life. So what we just did, we prepared these 3 equations and we solved them simultaneously to get to the final answer. Any doubts with this? Anyone? So I expect answers in yes, no, or still trying to understand, or maybe I will understand it if I watch the lecture once again.
Yes, ma'am, I got it.
Thank you, Sauri. What about Swapnil and Vanshita? Vanshita, are you there?
Yes, ma'am.
Okay, so I guess let's just leave it at this and call this the end of today's lecture. I will not try to cover much more.